All right, so good afternoon or evening, everyone, depending on where you are exactly right now. So welcome again to this Quantum Matter seminars. Today we have the pleasure to receive Salvatore Manmana. Thank you very much for accepting your invitation. And he's going to talk about photo-induced spinful excitations and Hubbard Hamiltonians with magnetic superstructures. Very interesting topic. And if anyone has a question, you can unmute yourself or you can type your question here in the chat box and we read for you. So everyone is very welcome. So thank you very much again, Salvatore. The stage is yours.
Thanks a lot. Thanks a lot to you for the invite. It's my pleasure to, well, at least be remotely with you and to talk to you and present some of the things that we have been recently doing. I remember I've been several times at Northeastern and I always enjoyed the visit. Let's hope we can repeat this at some time. But for the moment, let's do this online talk. As I just said to Adrian, I didn't prepare anything fancy or special to be broadcast on YouTube or to be recorded. But it's a standard seminar talk. But I hope you will enjoy it nevertheless, because I think there's some funny aspects which we can, of course, discuss about either during or after the talk. So let's get started. So the idea is to look at Hubbard systems, and then we do special excitation, and then the question is what happens, what kind of effects do we realize, what kind of excitations can we get. And this was done together with my PhD student Konstantin, who actually did all the hard work of doing the calculations and preparing the plots and so on and so forth. So okay. Yeah, now it's working. So let's start with some general overview. So what I'm interested in is the non-equilibrium dynamics of many body states. And in particular, there are many aspects. You can go to fundamental questions like, does the system thermalize, and so on and so forth. But here, I'm interested in one aspect which is relevant for experiments, modern experiments. Namely, I take a material and I highly excite it, and then ask what happens. And so the bottom line is what is known as probe experiments, which are pictured here. By the way, do you see my mouse? Good. Okay, excellent. So you have some sample which you're interested in, and then you hit it with a pump pulse, which can be as short as a few femtoseconds, and then with some time delay, you have a second pulse, which then hits the sample after the excitation. And then you can get some spectra like these, and then you have to interpret them, and you can understand what is happening on a femtosecond time scale if you do it right. And here in this particular case, actually what is happening is the dissociation of a hydrogen atom from a water molecule. And here you can see that this spectrum stands for a normal hydrogen molecule. And then after the excitation, if you wait long enough, then one atom here disappears. And here you can really make movies. That was amazing, of course, to study chemical reactions. But also, if you go to solids, there's a lot that can be investigated. For example, you can go to correlated states, correlated systems like mod insulators, and then ask basic properties of these. So you create some double occupancies, some holes. What is happening there? What has been exciting many people now for the order of 10 years or so is that people believe that in these setups you can realize and see transient state. So maybe long-range order is created, and one feature has been exciting many groups is that there are hints that superconductivity is obtained by these excitations, even above the critical temperature. Some groups claim that they see this even at room temperature. So only for a few picoseconds, but still, it's a signal. And then if you think further towards applications, you can ask the fundamental question, if you have some mod insulator and you do some excitation, then what about photovoltaic effects? And then Manusakis, about 10 years ago, asked if we can use mod insulators to make a PN junction, and can you get a higher efficiency? So this goes towards the so-called mod photovoltaics, which has the problems of their own, but never mind. Nevertheless, these belong to this class of systems and problems. So for us, or for me, I'm interested in numerical investigation of these strongly correlated systems, and then the question is actually how do I do that? So what methods do I need? What should they be able to do? And in this case, it turns out you need methods which are, well, as precise as possible, because we will be dealing with small effects. And they should be able to treat time-dependent Hamiltonians, and you should compute quantities which allow you to look at the formation of either long-range order, like in the superconductivity issue, or quasi-particles, as we will see in a few slides. So let's take on this picture for the quasi-particles. I mean, if you think of investigations which want to study the, let's say, nature or features of quasi-particles, then the best thing to do is to look at so-called spectral functions. So a spectral function is a response function where you disturb the system a little bit. For example, by taking out one electron in a macroscopic sample. And then you look at the response with time. Or if you like, you can also go to frequency space by a Fourier transform. And then if you go to frequency and momentum space, you get this what is typically called spectral functions. And here is an example for a so-called extended Hubbard model, which we will see later. And you see that you have many, many features, and they all can be interpreted as some kind of quasi-particle, which is found in the field theory. And so here in the numerics, by looking at some branches, or to be more precise, these are dispersion relations, you can identify if some particle is present in the system, or if your system hosts some quasi-particle. Now, what you can do is you can also go to finite temperature and heat up the system, and then ask for features in the spectral functions. And here, as I will show later, actually we found that for spin 1 Heisenberg change, so for pure spin system, we do get a new branch only by heating up. And last but not least, you can also go to other spectral quantities like this so-called optical conductivity, which I will introduce later, and ask for the optical response of the system. And this has been an important probe to see if you have superconductivity or not. And here, this is a plot from one recent paper of ours, where we computed this as a function of time, and we claim that it's not sufficient to see superconductivity. But that's another story, which I'm not going to tell you. And anyways, these are the quantities we aim for. That's what we want to look at and try to understand. No, that's the wrong direction, sorry. So now, how is this related to ongoing experiments? And there are some exciting developments, for example, also here in Göttingen, but I think also in other groups worldwide, that is concerning the so-called time-resolved ARPES. So ARPES is angle-resolved photo-emission spectroscopy experiments. And so roughly speaking, what you do is you have your sample, for example, here's some gold sample, you irradiate it, an electron is kicked out, and by measuring the angle and the velocity, you can conclude the spectral properties of the band structure of the material. And this you can do now out of equilibrium with femtosecond resolution if you really push it. And you can do it in 3D. And that's what people call a momentum microscope. So you can do kind of a tomography. And here you see now for this gold sample at different energies, what this band structure looks like if you excite it and then do this pump probe experiment. And then you see that you get several side bands, replicas of the original bands, and so on and so forth. And you can ask the question whether you can observe some non-trivial non-equilibrium states like Fouquet states, which are periodic replicas of the band structure and other things. Or they allow you to look in more detail at recombination processes and look into timescales and also to analyze the effects. So there's quite an excitement about these methods, and they are getting better and better with time. And One particular aspect that is studied with these is something that you know very well. And it's I feel kind of reading a textbook if I tell this, and that is to look at excitons. So just to remind you, what is an exciton? If you open your textbook, it will show you a picture like this. It tells you it's an electron-hole type excitation. So you have here a hole, here you have an electron, they are bound. And so you have here this electron moving around the hole or vice versa. In any case, it's one object, it's a quasi-particle, in which both electron and hole are bound. And then under circumstances, they can move through the lattice or they're static, and then you can use them for many things, for example, for photovoltaics. And here is now an example where this momentum microscope was used to look into exciton formation. And here you see in some more detail the setup and what they do in experiment. And so this the measurement apparatus. So you excite the sample, then an electron is kicked out, and you do all these funny things, and you obtain these pictures now. So this is the band structure, in this case of tungsten deselenide at equilibrium. And well, you get the band structure. That's cool. You can learn a lot of things already. But now let's do the excitation. And here you see the time axis. So let's have a look at time 0, which is the point when the peak of the photopulse arrives. And you see two new signals. So one at this K position and one at the sigma position. And if you wait a little, then you realize that the weight is scattered from the K to the sigma. So what is happening? And the claim is that what they see here is an exciton, which is formed by the photoexcitation. And then actually, due to scattering, for example, to phonons or whatever, you transfer weight to another exciton state, which is a dark exciton, which you cannot excite directly. But still it is some bound electron-hole pair. And then you can see in time how this dark exciton forms. And then you can study its properties. And so this is an interesting direction of research. But more generically, you can ask, what can we expect actually if we excite a system, and what can we expect to see in these spectral functions? And I think there are two directions. One, you can ask what happens if you heat up your system. And here is an example for a spin-1 Heisenberg chain. So that's a quantum magnet, and at very low temperatures, you find a spectrum which looks like this. So yeah, if you look more closely, you should have here two magnum continuum, which is very weak, so it's hard to see, but it's there. In this corner up here, you have a free magnum continuum, and then here, this black line, which is reproduced here, is a magnum mode, and then that's essentially it. You also see an edge state here at frequency 0. But now what is nice is that if you heat up the system, then you get a new branch. And here you see it best. So this is temperature essentially 0. That's temperature 1/2 J. And this new branch is due to scattering of magnets to each other. And so you get a new feature, and then you can ask, is this a new quasi-particle, or is this some scattering effect? And in this case, it's scattering. So it's not a new quasi-particle happening, but you clearly see that the excitation leads to, the scattering leads to such new features. On the other hand, if you now think again of these Poincare experiments and try to model a photoexcitation, people did this, for example, in this paper, which I will come back to later. And then here what you see is now the photo emission spectrum, not K resolved, only frequency resolved on this axis. And here is some waiting time. And you see for different values of the interaction that, that you can get new signals in between. And to make the story short, here they claim that these new signals are excitons. Why and how? Let's discuss it in a second. So, so when we do these non-equilibrium situations, or when we do excitations of these interacting systems, we have to be careful. What do we actually get? We get new branches, but then we have to understand where they come from and what they really mean. Now, talking about excitons. Excitons are usually treated mainly in the context of semiconductors. So if you like, weakly or non-correlated systems. But people have also studied these quasi-particles in strongly correlated systems like Hubbard models. For example, in this paper, which is now out of 20 years old, people looked at the so-called extended Hubbard model in one dimension, because there we have good numerical methods, and you can also do field theory and perturbation theory. And so they took a model in which you have the kinetic energy, so nearest neighbor hopping, some on-site repulsion, and then nearest neighbor and next nearest neighbor Coulomb repulsion, which they at the end truncate. I think this last term they usually is neglected. So sorry, so the basic idea is that the Coulomb interaction will lead to the binding between the particle and hole, and so you should be able to see here an exciton form. However, in such a strongly correlated system, other than in a semiconductor, the interaction will also determine the gap and the other features. I mean, it's a strongly interacting system. It's not a band insulator, but a mod insulator. And so you have to think a little deeper about what it means actually. And what they found is, if you go through the text, I'm not going to do that. So sorry, this slide was from a journal club, so I just used it for convenience. But what they find is essentially this story. So you have two Hubbard bands, which are separated by a big mod gap. And now, if you ask for exciton formations, if they do some perturbation theory and field theory, they find that, first of all, multiple excitons can be formed due to the interaction. That's already typically a difference compared to semiconductors. And second, they can be at different positions in energy. For example, they can be in the middle of one of the Hubbard bands, of the upper Hubbard band. So if you want to detect them, if you think of these experiments, this will be hard to find them. On the other hand, they can also be here in the gap. So this should lead to a new signal, which should be possible to detect in some suitable quantity. And that's what we're aiming for, that we look into the gap region and try to get new features and see if they have anything to do with excitons. And so now, how to identify excitons? Well, excitons are best seen in optical studies. I mean, exciton is defined as a quasi-particle formed by some photo-excitation. So let's do some optical measurement. For example, computing the optical conductivity, and then you should be able to see excitons. And that's what they did here. Already some 20 years ago, using DMRG and analytical methods, they computed these correlation functions, and then by computing the resolvent, they were able to obtain some frequency resolved quantity, which is called the optical conductivity, which I will also discuss a bit later. But here I'm only sorry, I came in the wrong direction. Here I only want to show you roughly what the story is. And if you do these calculations, you find here a gigantic peak in the real part of this optical conductivity. And if you look more closely and compare to field theory and perturbation theory, then you see that this peak is an exciton feature. So here, in this extended Hubbard model, as I understand, in equilibrium, without any further excitation, you get this gigantic response, which is due to the exciton which is formed in this mod insulator. And then you can ask, how big is this exciton, and is it bound, narrow, or is it widespread, and so on. So you look at certain correlation functions. That's what they did at that time, and then they can say if it's very narrow, then it's an exciton. But that's a detail. It's not so important. So questions. First, this is all in equilibrium. So what happens if we go out of equilibrium? Second, this is the optical conductivity, but what about these ARPES experiments? So can we compute something? to see it there. And indeed, well, some of you might know this paper. You can go ahead and you can compute time-dependent spectral functions, like Adrian and Tricia did here, using an approach where you couple to some bath, which you can explain much better than me, so I'm not going to do that. And if I understand correctly, your paper, what you see is some new additional features. I think in particular this one, and this one, and this is an exciton, as far as I remember. So you get what was predicted by the field theory. You have here Hubbard bands, which have a complicated internal structure, and then in addition you get this new mid-gap feature, which is an exciton. So it's possible to do these calculations and to find them in this ARPES, in these spectral functions, which are related to ARPES. That was in 1D. Can we go further? And one idea is, well, to go to 2D. And here people around Martin Eckstein and Philipp Werner used so-called cluster techniques to treat a 2D extended Hubbard model. And so what they do is they treat such small clusters by like 2x2 lattices exactly, and then they are embedded in some broader context, and then you can investigate various quantities like spectral functions. And so they modeled such a photo-excitation. So the photo-excitation will essentially lead to a double occupancy in the hole. So one electron moves over, and then you have the situation here. And now if you do photo-emission spectroscopy, then this means that you take out one electron. And so you have two possibilities. Either you take out an electron, which is here from a singly occupied site, that's the situation here, or you destroy the double occupancy and take an electron from this side. Then this leads to this situation. This means that you should have two different signals, because obviously here the double occupancy in the Hubbard model, you have to pay some on-site Coulomb repulsion. So this is on a different energy scale than taking out a single occupied site. And indeed, what they see is if you go to very large U at least, or to very large nearest neighbor interaction, as a function of time, you get here two signals, 1 and 2, which are associated to either the breaking of such a double occupancy or removing a single particle. And this you see only if the nearest neighbor interaction in this extended Hubbard model is strong enough, because it's this Coulomb interaction which leads to the binding between the particles. Okay, so what are we going to do? 2D is too difficult for me, so let's go back to 1D. But let's have a look at another variant of the Hubbard model, and that is one where we don't have long-range Coulomb interaction. So we have the normal Hubbard terms, only on-site Coulomb repulsion, but in addition, we have a magnetic background. So we have some magnetic superstructure, if you like. So our motivation originally came from manganites, where you can have some toy model, but actually you can also realize this in other situations like orbital selective mod phases, where you also have a two-band situation with a magnetic structure and so on and so forth. In any case, we have here now a model in which we have a non-trivial band structure, and where the Hubbard interaction will play. So the question is, what will happen? First question, will we be able to create quasi-particles at all? And second, if yes, what is this quasi-particle? Could this be an exciton? And so that's what I want to look at. And in order to be able, we now need to use methods. So the method that I'm using is MPS, matrix product states. And let me be extremely superficial because time is short. So let me only tell you the very basic idea. So the bottom line, in case you don't know these algorithms, is that you want to do data compression, but on a quantum state. So here is an example of a picture where you reduce the size of the picture by eliminating the irrelevant modes which cannot be resolved by your eye or by the screen anyways. And if you do it correctly, then you can compress it by a factor of 10, and you still have a good quality. If you reduce it too much, then you have bad quality. So, well, in any case, we can do this also for a quantum state. It turns out that entanglement is the key player. There's a lot of literature, a lot to be understood, very beautiful physics, but for time reason, I cannot dive into that. Instead, let me show you very quickly what is this ansatz. So matrix product states means that I take my many-body wave function. So I treat pure states, not density matrix, but pure states typically. And then I can rewrite them, or I can rewrite the coefficients of this wave function as a product of matrices. So what does it mean? Let's take, for example, a spin 1/2 chain, some Ising model or similar. Then here I would have 2 to the power of n coefficients, which are all complex numbers, which have to be stored. If I rewrite, then I will have 2 times n matrices. This means that I change the complexity to linear in the number of these spins. Of course, the matrices are still big, but now I can truncate them in a controlled way, and then I can optimize these states, and that's then what is going to be DMRG, density matrix randomization group, and so on and so forth, which are very powerful methods which work with an extremely high accuracy. Now, what do I need to do? Allow me to be a bit technical, but also to be quick. So we want to compute spectral functions. So what is this, or how to obtain it? You obtain it by computing such a propagator, like here, which, as you can see, has 2 different time arguments for the 2 operators. But then you do a Fourier transform over this time variable t prime, and you obtain this spectral function. And for non-inducting systems, this is exactly the band structure. Now, how can we go to time-dependent spectral functions? That's what we are interested in for the time-dependent ARPES. So here, what we do is the following. We introduce 2 time variables. One is a waiting time, which is here relevant for the state psi of t, which we obtain, for example, after arc range or after some excitation. So this is a non-equilibrium state that is realized only after this waiting time t. After this waiting time, or at this waiting time, we compute the propagator. But the propagator itself has a time dependence. This means we have a second time variable, t prime. And that's the time variable now, which we will use for Fourier transform, like here. And then at the end of the day, let me jump here to the last line, we will have one frequency variable, which comes due to this t prime, one time variable, which is this waiting time, and then the decay dependence. And so this is the way we compute them. And how to obtain psi of t? Well, we can, for example, perturb it at the beginning of the time evolution by applying some operator on some ground state, and then look at the time evolution. How do we do the time evolution? So this is more for experts. We use the so-called time-dependent variational principle, in which you compute the time evolution within this MPS manifold, but then you realize that if you do such a time step, as denoted here by this differential equation, then you will leave the correct manifold. But there's a way to correct this by projecting back into this good manifold that you're interested in. And so this works very well, very reliably. We find that this is the let's say, safest thing to do if you're interested in the spectral functions. And that's what we are applying all the time. And also more for experts, just quickly, why do we believe this is the safest thing to do? Here's an example of such a spectral function for this spin model. It's a spin 1/2 chain with some staggered magnetic field, not important where it comes from. And we compute the spectral function by doing this Fourier transform of over the time variable, as I mentioned before. And in this plot, you see many, many lines, which are all from different variants of time evolution algorithms for the DMRG. And we know that we have a gap here. On this line is omega equals 0. This means that from this line to some first feature, we should have no weight. And you see that many methods have some weight here. So these must be artifacts. The only one which has no real weight is this time-dependent variational principle. And so we take this because it's most reliable, and one can understand this because due to this projection, you eliminate some phase factors which can lead to artifacts in the spectral functions. And so this is what we use, and we believe that this also helps out of equilibrium to get more accurate spectral functions as a function of time. How we do this? Okay, here are some details. If you're interested in, we can discuss this later. At the end of the day, we perform 2 time evolutions. The rest, let's discuss later if you're interested. And now there are various issues with these. I should not hide them. For example, if you now think of these pump-probe setups, what exactly would you need to compute actually? And then, if you look more carefully, at least what people here in this paper suggested, is you need to compute this complicated expression. So here is this 2-time propagator that I just introduced. Then you have several matrix elements. You have the Fourier transform, and then you have 2 envelope functions, which is the shape of the pulses, which is strictly a Gaussian. And these need to be included also, and then you have to perform this complicated integral. Now, this seems to be well defined as long as these 2 functions don't overlap. But if they overlap, then you have a problem with some gauge degree of freedom, and then notion like momentum apparently gets problematic. And so people are still working hard on this issue, and one needs to think on how to define this Fourier transforms, and then one needs to be very careful. That's one thing. The other thing is, well, we have 2 time axes. So how and why do we the Fourier transform the way we do it? So let me illustrate this. So we have here the 2 arguments, so T1 and T2 of our propagator. And then if you, in principle, you could choose, for example, to integrate over this line and define your omega by doing a Fourier transform along this direction. However, what we do is the following. So we increase both arguments in the same way until some waiting time. Then we keep one of them fixed, and then we increase only the second one. And then we do the Fourier transform over this green bar. This is what is called relative time coordinates. Alternatively, you could also do the propagation until here, and then go in orthogonal direction like this, and then do the Fourier transform over this coordinates. That's what is called Wigner coordinates, which is also sometimes used. And now it turns out that for the MPS, if you use Wigner coordinates, you have to store many, many more states. It's much more complicated. It's much more effort. So for the sake of simplicity, we prefer relative times. And now you can ask, is this a problem? To be honest, I don't know. But if you look at papers like this one and talk to people, then they say that the results are essentially the same, irrespective of whether you take Wigner coordinates or relative coordinates. And so we take it easy, or we take the easier path and do the Fourier transform over this relative time coordinates. Okay, so now I think I have something like 10 minutes left. Let's see if I can show you some of the results. So what are we doing now? So we are interested in this exciton formation. So well, let's model photo excitation, similar to what is done in this semiconductor business. So we take a system which has multiple bands, and then we excite one electron from the lower band to the upper band in a direct transition. So no momentum transfer, nothing, it just moves up. And so this means that we perform a perturbation with an operator which looks like this. So we destroy a particle at momentum k in band nu with a spin sigma, and we create it in another band. And here you see that we have the freedom to pick the spin direction. So we can choose actually only one spin direction to do that, and we will do that. We find it useful to do that. And then you realize, okay, for non-interacting systems, that's very well defined because there you have a band structure. But for interacting systems, you need to be more careful because here this notion of band structure is actually not exact anymore. And scattering will definitely influence the effect of such an operator. And well, after we do this calculation, you see this is k and omega resolved. This means we need to look at the time-dependent spectral functions. And well, that's what we're going to do now in a Hubbard system where we identify separate bands. So why do we use spin-selective excitations? So here, once again, the system we're looking at. So that's a Hubbard chain with this magnetic background. And long story short, we find that if we excite only one spin direction, then in real space, we get a periodic pattern. That's a charge density wave pattern, which is formed. If we excite both spin directions, this is not happening. So there's something interesting happening if you only go into one spin direction, and that's what we are curious about. And so we follow only one spin excitation. So now let's come to the results finally. Let's start with tests and benchmarks. And here you see an equilibrium situation. That's this Hubbard model, but at u equals 0, no interaction. And we just computed this propagator and then did the Fourier transform and obtained this result. And the green lines, they are the band structure for this non-interacting system. And you see that the bands that you obtain in equilibrium, they agree very well. So the method works in equilibrium. And here, oops, sorry, that was wrong. No, another direction. So here, let's look at a cross section. And this here is just the results along this line. And you see, actually, you should have delta peaks, but they're smeared out. That's because we have a finite resolution. We have to introduce a broadening. And here, we do not push for the highest resolution, because out of equilibrium, it's actually a lot of calculations that you need to do. But we aim for a resolution which is good enough to see the effects. And that's and here, that's the picture that we have in mind. So now let's go to the interacting system. So we have u equal 4, and this staggered potential is 2 times the hopping. And let's look at quarter filling and half filling. So quarter filling is here the lesser spectral function and here the greater. And you see in the lesser spectral function, there's nothing. This essentially looks like the non-interacting system. In the greater, however, we have many features, so interactions do play. That's one thing. Then let's go to half filling. And here you see that already in the lesser spectral function, you have several new features if you look more carefully. And due to particle hole symmetry, they are reflected also in the greater spectral function. Sorry, I'm always going the wrong direction. So here we go. If you look at cross sections, you will realize that you have essentially 2 regions. One where the lesser spectral function lives. This is what I call the lower Hubbard band, and then another one where for the greater. And you have a fine structure, so you have multiple peaks inside. And you see this for different values of the interaction. So also for u equals 16, here it's maybe more drastic. So here you see this region is the lower, what I would like to call lower Hubbard band. And here, this is what you might call the higher, the upper Hubbard band. And in addition, you have these peaks, which are from the band insulator, which is underlying. And so we call this a correlated band insulator. And where do correlation effects actually play a role? So what you see here is these peak positions as a function of u, as obtained for a very small system, 1 unit cell. And what you see is that well, the 2 main bands, they survive up to rather strong interaction strength. But in the meantime, you get additional peaks, additional structures, and these are all Hubbard satellites that are formed due to interaction effects. Also this one, which is pretty strong. And so we could say that we have 2 peaks which are due to the non-inducting band structure. So that's just a renormalized band structure plus at least 1 Hubbard satellite. And then for very large U, this takes over, and then the Hubbard satellites become more important. So now let's come to the excitation. So we apply this particle-hole excitation, and as you can see, we indeed shift weight to the next band. So you see this also here in the cross section. Originally the peak was here, and now it's shifted over here. So this is at U equals 0. So everything works as expected. So we have a good quality of our results. We can work reliably. And there's a side remark. We're using open boundary conditions. And in order for this to be time independent, because at U equals 0, this should be time independent because we're just populating eigenstates, we have to be careful that we do the Fourier transform to momentum space using eigenstates of the non-interacting system. So that's a bit tricky, one needs to be careful, but if we do that, we see that we get a very precise time evolution where this system is very stable. And so again, once again, we are confident that we have a good resolution. Now let's go to the interacting system. And let's look at the instant when we do the excitation. So here, first quarter filling. We do the excitation now only in one spin direction, in the spin-up direction. And we only look at the lesser spectral function. And here you see, okay, we move one particle up and nothing happens. In the spin-down direction, you see nothing. It looks like the ground state. However, if you do the same at half filling, then once again you see, okay, we move some weight in the up direction, but in the down direction, we have here some shadow. And so you could say, yeah, maybe it's nothing, it's very small and so on. But actually, there is something. And this is what I'm going to talk about next. Let's have a closer look at what is actually happening. So here, once again, let's have a look at the cross section. So originally, in the up direction, the peak was here. Now it's moved to the position of the greater spectral function. But you see, not completely. So something remains. And this is because now we are dealing with an interacting system. So this particle-hole excitation, the way we introduced it with these operators, it's not perfect. So this is our correlation effect. But nevertheless, to a good approximation, we moved one particle to the upper band. Now, the surprising thing is that in the down direction, we get this feature here, which you would not expect naively. I mean, where should it come from? And let's have a closer look, for example, by going to much larger interactions. So this is now U over T equals 16. Here, once again, you see in the spin-up direction, the weight is transferred to the greater spectral function as expected. But in the down direction, we have now a clear peak just below this region of the upper spectral function. So that's a mid-gap state which is created. And if you can also look at it looking at the atomic limit, and there you would expect actually a feature at U minus delta half. Here it's at about U minus delta. So it doesn't perfectly agree, but there seems to be some excitation which you can capture also in some limiting case. And now if we look at the time evolution, what we see is in the up direction that this excitation now starts to spread and to spread over the band here. But also you have some recombination, so some weight goes down. And in the down direction, we have this new feature, and it remains. It's very stable. So at least on the time scales that we can treat, so this is 20 in units of the hopping, this is very stable. So what is this? And to further investigate this, we compute the optical conductivity as suggested by Essler, Gebhardt, and Jeckelmann, the paper from 2001. But we compute it out of equilibrium. And to do so, we have to look at some tricks. And one useful approach is that we do this by computing the current after our probe files, and then dividing the current by the vector potential that we introduced in a so-called Pire substitution ansatz. So the motivation for this is the basic definition of the optical conductivity, which is here that the current, the response current, is proportional to the electric field and the conductivity. The electric field is the time derivative of the vector potential, and then if you plug things together, then you obtain this quantity. So with the DMT, we need to compute these currents. This can be done rather well, and then you obtain the optical conductivity. And if you do that, then you see that for all values of u, you get a new peak here. And under circumstances, you get also multiple peaks. So in the gap region, you get not only one peak, but more than one. Second, we do the excitation in the up direction. So sorry, I should have explained. So the red lines are the optical conductivity in equilibrium, so before the excitation, and blue is after this photo excitation. And we see here that we have some feature at small omega, but this is some band transition, which is not relevant. But these new peaks over here, they are not obtained in the up direction, so they're only in the down direction. And now, if you think of this interpretation, that such a peak is related to an exciton, this really looks like we created excitons in the down direction, so opposite to the direction that we excited. And can we understand this? And actually, yes, we can see at some mechanism where the binding comes from. So let's imagine that we formed a particle, a doublon-hole pair where next to each other. Now, what happens if we want to separate them? Then you realize that, for example, if you want to move the hole over here, then this electron needs to go down. Now, due to the magnetic background, this costs energy, namely this delta. So this will cost energy, and this will not happen. On the other hand, if you want to move the double occupancy, you have to move the electron which is pointing in the wrong direction, so to speak. So once again, this will cost energy. And in any case, whenever you try to move either the double occupancy or the hole, you have to pay this amount delta, and you have to pay it for each motion. This means that you have a binding which is proportional to delta times the separation. So this is now really like a string, and so the particles do not want to separate. So you do have a binding due to the staggered potential and due to the Hubbard U, and this is an exciton. In addition, you can see in second-order perturbation theory that this doublon-hole pair can actually move with a finite amplitude, which I think is proportional to T over delta or something like that. And so these are all features that we expect from an exciton. And so with this, and let me summarize. So what we did was that we used matrix product states to compute time-dependent spectral functions and optical conductivities. At least the testing cases that we did, this worked very well. For the non-interacting systems, we know what to expect, and we got exactly what we wanted. We don't see any artifacts like negative weights or similar, at least in the spectral function not. So we are confident that we get the right picture. For this particular system, if we do this spin selective electron-hole-like excitation, then we get this new in-gap feature, but only in the opposite spin direction. And we can interpret this as an exciton because we find that there's some binding of doublon-hole pairs. Yeah, and with that, thanks for your attention, and now I'm happy for your questions.
All right. Crisia, you there?
I am. I was waiting for questions.
I got one, if you guys can hear me.
Mm-hmm.
Yeah.
Hey, Salvatore. The equilibrium ground state excitations for this Hubbard model are well described by beta ansatz. I wonder if you've thought about trying to set up a situation where you could compare in the non-equilibrium situation to some kind of beta-ansatz calculation. And you mentioned field theory and perturbation theory before.
Right.
Maybe those are more, in the short term, more practical, but the beta-ansatz is nice in that you don't have to fit out so many parameters.
Right, but the beta-ansatz, of course, works only for the normal Hubbard model, right? I mean, the extended Hubbard model is not beta-ansatz integrable.
So what if we turn off delta, I guess I'm asking?
That's the question. So I think also the delta breaks the probability, to my knowledge.
Yeah, so turn it off. So can we do a simulation where we can make a comparison?
Yeah, you mean as a benchmark for the calculations? Or?
Yeah, well, to try and understand.
So sure, yeah, one should do that. I mean, it gets tricky because already this notion of a particle-hole excitation, if you don't have a non-intact band structure, it's difficult to introduce this. So you should think of another type of excitation. But maybe
something simple. I mean,
a quench, maybe.
So we're thinking about, let's say, the nearest neighbor Hubbard. I mean, the nearest neighbor hopping Hubbard model with on-site repulsion at half filling, right? It's a mod insulator, so we want to think of a simple excitation where you can compare. What it seems like the natural thing would be, I don't know, created a double excitation and a single excitation on nearby sites or something.
This one can do. Yes, but this is of course in real space, so that's not exciting over a band gap, but that's some local excitation in real space. Yes, okay. And then when one can ask for the dynamics, that would be interesting.
In the case of beta-ansatz, we have all the excited states as a function of U and T and all that, you know.
Right.
So it seems like we could compute everything.
That's right. But can you also compute the spectral weights? I thought that's all difficult for beta-ansatz.
Yeah, of course.
Right. Yeah.
I just have a comment, not a question, because you know I always was puzzled by the the lack of agreement on which Fourier transform you should take, right? And you know, you mentioned that there is debate in the literature and people actually discuss different approaches and compare, but when you actually write your
specificals, how we make a right.
Right.
Let's okay, let's mute Noah. All right. So when you actually do your perturbation theory, time-dependent perturbation theory to calculate your time-dependent structure spectral function, there shouldn't be let me put it this way, you know, the experiment shows you something and you're trying to describe the experiment, right? So there has to be one approach that allows you to directly compare to experiments and should be the right approach. That's my point. But no, I just wanted to mention that the time-dependent tunneling approach that we presented and you showed us actually doesn't rely on Fourier transforming, right? So it's actually simulating the actual scattering event, the experiment, and it doesn't rely on, well, it avoids this caveat. Let's put it that way. It would be interesting. It would be interesting to compare our approach to your two-time approach and see if they agree and it would be a nice confirmation.
I totally agree. And I mean, one could try to see if it's true that it doesn't really matter whether you take these Wigner coordinates or these relative coordinates, as people claim in the literature. Yeah, that would be very interesting. And,
now, another question that I have is this model that you're using here, is it related to some real experiment, or you mentioned this paper with this one-dimensional material, but I'm not sure if the actual material is one-dimensional, but you showed this octahedra.
Yeah, let me
and
go to the slide. Oops, here it was.
There, you passed it.
I passed it. Okay, let's see. Yeah, here it is. Yeah. So, well,
these interpolars. Is this an actual? I mean, you're trying to describe an actual experiment here, or it's a toy model? That's
so we looked at manganites, which are 3D materials, and they can be thought of, or some phases can be considered as a crystal of this kind of polarions, of different polarions. So there one can have a closer look. But this 1D version, that's a purely toy model for the manganites. Now, I think Elbio and what's his name, Jacek, and other people claim that some ladder systems, I don't remember if it was iron peptides or some others, they host so-called orbital selected Mott phases. So what is an orbital selected Mott phase? That is that one band shows some magnetic pattern, like this 2 up, 2 down, and the other band is some itinerant electrons. And so that's similar to this one. It's not exactly this model, but I think it's similar. So some phases, I believe they might host a related model. So that's maybe the closest to experiment if you ask for this model. Otherwise, it's a toy model which is convenient for us to play around. But actually,
and the kind of excitons that you showed us today, have they been actually experimentally observed in systems such as manganites or others?
Not that I knew.
Are you aware of them?
Yeah, I'm not aware of. I mean, look, my picture is that you need nearest neighbor or long-range Coulomb repulsion to get excitons. So I was a bit surprised to see here an exciton without long-range interaction. On the other hand, there are so many semiconductors. Maybe already there someone has looked at some similar situations. So I cannot exclude it that this is observed somewhere, but I'm not aware of. And for the manganites, I should talk to the experimental guys, but I'm not aware of also. I mean, this is a fresh finding, so to say. Yeah.
Thinking, I mean, if you think of this as a 2-band model, right? You have this band splitting here, so that's reasonable. Well, there are 2-band models like the one that LBO discusses have a Hund interaction, and the Hund interaction, I think, can give you excitons, but
yeah. So
I wonder if there is a connection between the.
I mean, this delta actually is the Hund excitation, Hund interaction in some mean fields. So this is the Hund term in some mean field approximation. So yeah, maybe it's related to that. Yeah. So you're saying that excitons can be caused by Hund interaction in multiband models, or okay.
Yeah, that's correct.
But okay, then I have to look at this and see if it's related to this one. I just don't know. Maybe.
But the thing is that when you have the these 2 band, you also have a U and U prime. You have a U prime in between the 2 bands, and this can be thought as your long range interaction, if you want. So that might be a way to connect the 2 ideas.
Right. But here we don't have explicitly a long range term, so but it works nevertheless.
Any other questions from the audience?
Okay.
All right. If not, I guess I'll be in charge of wrapping up. We thank Salvatore once again for joining us this late in Germany. Thank you for staying late in your office and just for us. I appreciate it. And I thank the audience for joining us today as well. And we'll see you again next week for another Quantum Matter seminar. Yeah. Goodbye, everyone.
Yeah. Goodbye, and happy Thanksgiving. Yeah. See you.